Let's look at the second part of this example. Once again, we have a rod on the x-axis, and we're trying to find its center of mass, but this time it's a non-uniform rod. That means that the mass is not evenly distributed throughout the length. We're given that it has a length L and a mass per unit length lambda equals alpha x. Remember from the first part of this problem that lambda is the mass per length. It's the linear mass density. We're trying to find the center of mass. We know it's going to be along the x-axis, since the center of mass in the y and z directions is 0. So let's find the position of the center of mass, the x-coordinate. We're going to use the same equation that we just used, 1 over m integral x dm. We're going to make the same substitution that we just made, where we write that dm is equal to lambda dx. This time, the linear mass density is not constant. We cannot take it out of the integral. We have to write down its definition. It's defined as alpha x. Alpha is a constant. We know that this integral runs the length of the rod from 0 to L. We can go ahead and take out alpha, take it out of the integral. Then we're going to integrate x squared. We're going to integrate x squared, which gives you x cubed over 3. And the limits are from 0 to L. So we're going to get alpha L cubed over 3m. When you plug in 0, you get 0. That's supposed to be a 3 here. So we were done last time after this step. However, we always want to give our answer in terms of the variables given in the problem. For this part, m is not given in the problem. So we're going to want to write the mass in terms of the linear density and hopefully get rid of m. We really want our answer to only be in terms of L. We saw that when our rod was uniform, that the center of mass was in the center, that point. Now, where do you think the center of mass is going to be? We have a non-uniform mass distribution that depends on x. That means as x gets bigger, the mass density gets bigger. X gets bigger to the right. That means that for this rod, there is more mass on the right side of the rod than on the left-hand side. So our center of mass should be closer to the end. So in order to find m, what we can do is we can write a different integral. Remember that when we're doing this integral, this dm here, it's the mass of one very small element. And we said that we're integrating over all of these elements to get the whole mass. So big M is the integral of dm. If you integrate over all the little mass elements, you get the total mass. So that's how we find m. We can make the same substitution that dm is equal to lambda dx. We can once again plug in our lambda as alpha x. I'm going to integrate from 0 to L. We can take out our alpha, our constant. We're going to have the integral of x dx, which is x squared over 2. From 0 to L. We can plug in our limits of integration. We're going to get alpha L squared over 2. So now we have an expression for m and an expression for the center of mass. Now all we need to do is plug this expression that we just found in for m. So we're going to have that the center of mass position is alpha L cubed over 3m. So we're going to plug this in for m. It's going to be alpha L squared over 2. And now we just need to do a little bit of algebra. We know that when we divide by a fraction, we can multiply by the reciprocal. So we're going to get alpha L cubed over 3 times 2 over alpha L squared. We're just going to multiply by the reciprocal here. And that allows our L squared to cancel out here. We just have L on the top, our alphas cancel out. And we're left with 2L over 3. So that makes sense. Our center of mass position, instead of being at the center as it was for a uniform rod, is going to be closer to the right-hand side now because there's more mass concentrated on that side.